Welcome back. In the last lecture I discussed capillary tubes and automatic expansion devices. In this lecture I shall discuss the rest of the expansion devices. So, the specific objectives of this particular lecture are to explain the working principle, features and performance characteristics of thermostatic expansion valves, explain the working principle of float valves, explain the working principle of electronic expansion valve, and discuss some practical issues. At the end of the lecture you should be able to explain with a sketch the working principle of a thermostatic expansion valve, explain its performance characteristics and variations available, explain the working principle of high and low side float valves, explain the working principle of electronic expansion valves, and finally discuss practical issues to be considered while selecting expansion devices. So, let us discuss first the thermostatic expansion valves, abbreviated as TEV. The thermostatic expansion valve is the most versatile among all the expansion valves. It is most commonly used in refrigeration systems. A thermostatic expansion valve maintains a constant degree of superheat at the exit of evaporator. It does not maintain a constant temperature, but it maintains a constant degree of superheat at the exit of evaporator. Thus, it protects the compressor by ensuring that no liquid enters into the compressor. This is the biggest advantage of thermostatic expansion valves. So, now let me describe the working principle of a thermostatic expansion valve. A thermostatic expansion valve consists of a feeler bulb attached to the evaporator exit tube so that it senses the temperature at the exit of evaporator. The feeler bulb is connected to the top of the bellows by a narrow tube. The feeler bulb and the narrow tube contain some fluid that is called as power fluid. The power fluid may be the same as the refrigerant used in the system or different. Okay. So, now let me show the picture of that. This shows the schematic of a thermostatic expansion valve. You can see that this is the inlet to the valve. So, the high pressure refrigerant liquid from the condenser side enters into the valve at this point, then it flows through this orifice and its pressure reduces across the orifice, and the low pressure refrigerant flows out through the valve and enters into the evaporator. It takes the heat from the surroundings, it becomes a vapor and goes out to the compressor. Okay. Now, if you look at the valve, as I've already mentioned, this valve consists of a feeler bulb. This is the feeler bulb, and this feeler bulb is attached to the suction line, that is the exit of the evaporator. Okay, so there should be a good thermal contact between the feeler bulb and the refrigerant tubing, and the feeler bulb is connected to the thermostat body with a narrow capillary tube. Okay, so the capillary tube connects the feeler bulb to the thermostat body. Okay, and the feeler bulb, the thermostat space above the bellows and the capillary tube are filled with a fluid called as power fluid. Okay, so this entire space plus this space in the capillary tube and this entire feeler bulb space is filled with a power fluid. Okay, the power fluid can be same as the refrigerant or it can be a different fluid. Okay, and if you look at the body of the thermostat, you will see that it consists of a bellows. Okay, these are the bellows. You can also use a diaphragm. Okay, it can be either a diaphragm or a bellows, but I have shown here a bellows, and this bellows is connected to a needle stand. Okay, so you have the needle stand here. So bellows is directly connected to the needle stand, and you have the needle, and this the position of the needle decides the area available for the refrigerant flow. Okay, at this point the area available for the refrigerant flow depends upon the position of the needle stand, and the position of the needle stand in turn depends upon the balance between various forces acting across the bellows. For example, if you look at the bellows, the downward force is Fp, okay, and this Fp is due to the pressure of the power fluid. Okay, so if you can write Fp is equal to some Pp into AB, where Pp is the pressure exerted by the power fluid and AB is the area of the bellows. Okay, so this is the force which is trying to push the bellows down, and trying to push the bellows down means the needle stand also will be pushed down. And what are the forces opposing this motion? The forces opposing this motion are, first, because of the evaporator pressure, that is Fe. Okay, this is a force, upward force due to the evaporator pressure. This is equal to PE into AB, where PE is the evaporator pressure. And in addition to that, you also have the spring force Fs. Okay, so spring force Fs is acting upwards, and force Fe due to evaporator pressure is acting upwards, and the force due to the power fluid is acting downwards. Okay, so the point at which the balance takes place is the steady state, and at what point the balance takes place, that decides the area available for the refrigerant flow through the orifice, which in turn decides the refrigerant flow rate. Okay, so this is the construction, and you can see that there is an adjustable screw here, and using the screw you can adjust the stiffness of the spring. That means you can adjust the force exerted by the spring, okay, by turning the screw. So that's what I have already explained, and under normal circumstances the pressure of the power fluid PP is the saturation pressure corresponding to the temperature at the evaporator exit. Okay, so let me go back once again. So the pressure acting here, let us say that is PP. This pressure corresponds to the saturation pressure. That means PP is equal to P saturated pressure corresponding to the temperature existing at this point. If you are assuming that there is a perfect thermal contact between the feeler bulb and the refrigerant tubing, then the temperature inside the feeler bulb will be same as the temperature inside the refrigerant tubing. Okay, that means this feeler bulb temperature also will be Ts. And if you have a two-phase fluid inside the feeler bulb, then the pressure exerted by the power fluid is nothing but saturated pressure at this temperature, that is P sat at Ts. Now the force, so this is I have already explained to you, the force Fp exerted on top of the bellows of area AB is given by Fp is equal to Pp into AB, and the force exerted below the bellows consists of, as I have already discussed, first the force due to evaporator pressure Fe, and force exerted by the adjustable spring Fs, and force due to evaporator pressure Fe is given by Fe is equal to P into AB, where AB is the area of the bellows and P is the evaporator pressure. Okay, evaporator pressure at temperature TE. Now in steady state there will be a force balance on the needle stand. That means Fs is equal to Fp minus Fe. This is because we have seen that the downward force is equal to Fp. That should be equal to the upward force. This is the force acting in the downward direction. This should be equal to the upward force. Upward force is Fe plus Fs. Okay, so that means Fs is equal to Fp minus Fe. Okay, and this is equal to, you can write this in terms of AB, that is bellows area, into pressure acting on the bellows due to the power fluid, minus evaporator pressure PE. Okay, so at steady state finally you have Fs is equal to AB into Pp minus Pe. Once the spring force F is fixed, then Fs is equal to Fp minus Fe is equal to constant. That implies that Pp minus P is equal to constant, because the area of the bellows remain constant. Okay, so once you set the spring force, then the difference between the downward pressure and the upward pressure will remain constant. Now since Pp is the saturation pressure of the power fluid at evaporator exit temperature Ts, and P is the saturation temperature of refrigerant at evaporator temperature Te, Pp minus P is constant implies that Ts minus Te is equal to constant. Okay, that means once you fix the spring force, and if you keep the spring force constant, then the difference between the downward force and the upward force remains constant always, and this is proportional to the pressure acting on the above the bellows and pressure acting below the bellows, difference between these two pressures, and these two pressures are nothing but the saturation pressure corresponding to the exit temperature and the evaporator temperature. Okay, once the pressure difference is constant, that means the temperature difference also should be constant, and this temperature difference is nothing but the degree of superheat. Okay, so Ts minus T is constant means degree of superheat, that is delta Ts is constant. So, for a given spring force Fs, the thermostatic expansion valve maintains the difference between Fp and Fe, or the degree of superheat delta Ts constant always. However, the degree of superheat can be adjusted by adjusting the spring force. And we have seen that the delta Ts, that is the degree of superheat, is proportional to spring force Fs, which is equal to Fp minus Fe. Okay. So, if you increase the spring force, the degree of superheat increases. If you reduce the spring force, degree of superheat reduces. Since the spring force is finite, a minimum degree of superheat is required to open the valve. So, if you once you have the spring, it always exerts a finite amount of force. Okay, it can never become 0, right? That means Fs is always greater than 0. Fs is always greater than 0 means Fp minus Fe is always greater than 0. That means Pp minus Pe is always greater than 0. Okay, and Pp minus Pe is 0 means degree of superheat should always be greater than 0. That means you should have a finite amount of superheat only when only then the valve can open. Okay, so that is the meaning of this. So this is shown in this picture. So you can see that here the degree of superheat delta Ts is plotted in the x-axis. Okay, and on the y-axis you have the percent opening. Okay, percent opening of the valve. When the percent opening is 0, that means the flow rate is 0. Percent opening is 100%, means the mass flow rate is maximum. Okay, so I was mentioning that at this point degree of superheat is 0. Okay, once the degree of superheat is 0, you have Fs is equal to Fp minus Fe, right? This, as I said, is always greater than 0. Okay, so this is greater than 0 means you have a net at this condition when delta Ts is 0. Okay, there is a state of imbalance. That means there will be a higher downward force. Okay, this higher downward force will close the needle. Okay, if you look at the needle, you have the needle like this. Okay, so this is the needle. So this needle will be pushed upwards because of the spring force. Okay, that means it will be completely closed. So if you want this to open, you must provide some minimum degree of superheat delta Ts. Okay, so if you, as you go on increasing the degree of superheat, it will not open till it reaches a minimum value. Only at this point the needle starts moving downwards. Okay, only then you will have some finite mass flow rate. Okay, and normally the spring force is set in such a way that a minimum degree of superheat of about 4 to 5 Kelvin is required to open the valve. Okay. Now let me give a small example. Let us say that we have a thermostatic expansion valve which uses power fluid as R12 and the refrigerant is also R12, and the evaporator temperature is 4 degrees centigrade. And the evaporator pressure, which is nothing but the saturation pressure at 4 degrees centigrade from the refrigerant property database, is found to be 250 kilopascal. Let us say that the pressure exerted due to the spring Ps is 60 kilopascal. Okay, so we know the evaporator pressure Pe and the spring pressure Ps. So we have to find out what is the degree of superheat. So it is a very simple problem. At steady state, we know that the downward pressure Pp is equal to Pe plus Ps. Okay, so P is equal to 250 kilopascal and Ps is 60 kilopascal. So Pp is equal to 310 kilopascal. Okay, so Pp is nothing but the saturation pressure corresponding to the exit temperature Ts. Okay, so we know the saturation pressure. So again we can find out what is the corresponding saturation temperature. Okay, so if you look at the refrigerant property table, you find that at 310 kilopascal the saturation temperature of R12 is 9 degrees centigrade. That means Ts is 9 degrees centigrade. Once Ts is 9 degrees centigrade, the degree of superheat, that is delta Ts, is equal to Ts minus Te, that is equal to 9 minus 4, which is equal to 5 Kelvin. Okay, so that means this valve has a degree of superheat of 5 Kelvin. Okay, this is decided by, you can see that from this example, this solely depends upon your spring pressure. If you increase the spring pressure, you will find that the degree of superheat increases. Now let us look at the effect of load variation. How does the valve adjust to different loads? First, let us look at the increase in refrigeration load. What happens when load increases? If the load on the plant increases, the evaporation rate of refrigerant increases, the area available for superheating the vapor increases. As a result, the degree of superheat increases. Okay, the degree of superheat increases means the pressure of power fluid Pp increases. Why PP increases? Because once the degree of superheat increases means the temperature at the exit of the evaporator Ts that increases, and this temperature is sensed by the feeler bulb. Okay, that means the feeler bulb temperature increases. Once the feeler bulb temperature increases, the power fluid which is stored inside the feeler bulb, its temperature also increases. Once the power fluid temperature increases, its pressure increases. Okay, so ultimately when the load increases, the pressure in the feeler bulb increases. This pressure is acting on the bellows. Okay, so the pressure acting on the bellows increases when the load increases. So what happens when the pressure acting on the bellows increases? So when the pressure acting on the bellows increases, needle stand is pushed down and the mass flow rate of refrigerant increases. Okay, you can see here that as I was telling you, let us say that this is the temperature Ts. Once Ts increases, this fluid becomes warmer. Once this fluid becomes warmer, the pressure inside increases. That means the pressure acting on the bellows PP increases. So the balance is disturbed momentarily. Since this pressure increases, the downward force Fp increases. Once the downward force Fp increases, this needle stand will be pushed down. Okay, that means this portion will be pushed down. Once this is pushed down, you can see that the area available for refrigerant flow increases. Once the area available for refrigerant flow increases, more refrigerant enters into the evaporator. Once more refrigerant enters into the evaporator, this temperature reduces because the degree of superheat reduces. Once the degree of superheat reduces, this pressure also reduces. So again a new this comes back to the original pressure. Okay, again the degree of superheat delta Ts is restored. Okay. So degree of superheat is restored, and this is the ideal case, right? Now what happens when the refrigeration load decreases? We know that when the refrigeration load decreases, less refrigerant boils, that means degree of superheat decreases. Once the degree of superheat decreases, pressure applied by the power fluid above the bellows decreases. This is because the temperature of the power fluid decreases, so pressure also decreases. Once the temperature of the power fluid decreases, needle moves up. This is opposite to what happens when the load increases. Okay, this force reduces. That means momentarily Fs plus Fe will be greater than Fp. Once this is greater than Fp, this will move up. Okay, once this moves up, actually the spring force reduces and a new balance point is established, and at this new balance point the area available for refrigerant flow reduces because the needle has moved up. So once it moves up means area available for the refrigerant to flow through the orifice reduces. Once the refrigerant flow rate reduces, the superheat increases. That means this temperature again increases. Once this temperature increases, pressure in the power fluid PP increases. Okay, so as Ts increases, PP increases. Once PP increases, Fp increases. Okay, once Fp increases, you will find that again balance is restored. Okay, Fs plus Fe will become Fp, right. So this balance is restored at a lower flow rate. Okay, so that is what you have to keep in mind. So mass flow rate of refrigerant decreases. So degree of superheat is again restored due to this. Thus a TEV always establishes balanced flow condition between compressor and itself. Okay, that is why this is a very effective expansion device. Okay, so the refrigerant flow rate is always proportional to the load. So that is the reason why the thermostatic expansion valve is most versatile and it is very effective. Okay, so it is something like a closed loop control. Okay, so it takes the feedback from the feeler bulb and takes a corrective action, and this corrective action is in the line of our requirement. Okay, that means when the load increases, it increases the flow rate to meet the increased load. Similarly, when the load reduces, it reduces the flow rate to meet the reduced load. Okay, so in addition to providing the required pressure drop, it also controls the flow rate in a required manner. Okay, this is unlike your automatic expansion valve, which I discussed in the last lecture, where you find that when the load increases, actually the refrigerant flow rate reduces. Okay, whereas when the load reduces, refrigerant flow rate increases in the automatic expansion valve. Of course, in automatic expansion valve, evaporator temperature always remains constant. That will not be the case in thermostatic expansion valve. Thermostatic expansion valve, when the load varies, the balance point occurs at a different evaporator temperature, but what remains constant is the degree of superheat. Okay, so that is the difference between these two types of valves. Now let us look at variations available with the thermostatic expansion valve. First variation is that thermostatic expansion valve with external equalizer. In large evaporators, the pressure drop across the evaporator can be significant. Then the saturation temperature of refrigerant at evaporator exit will be saturation temperature at evaporator exit is nothing but saturation temperature at exit pressure okay. So TE exit, this is saturation temperature at the exit of the evaporator. This is nothing but the saturation temperature at this exit pressure, and exit pressure is nothing but inlet pressure minus delta P. Okay, delta P is the pressure drop across the evaporator. When this pressure drop across the evaporator is negligible or 0, then you find that exit temperature is same as the inlet temperature, because exit pressure is same as the inlet pressure. But you find that in large evaporators, especially single path evaporators, delta P can be very high. Okay, once delta P is very high, this difference will be large, and you will find that the exit temperature will be inlet temperature minus some delta T. Okay, and this delta T is proportional to your delta P. Okay. So if superheat delta Ts corresponds to evaporator inlet pressure and temperature, then effective superheat is equal to delta T effective is delta Te plus delta Ts. Okay. So COP will be low and the evaporator surface is poorly used if delta T effective is large. What it means is, let us say that you have selected a thermostatic expansion valve which senses the inlet pressure of the evaporator, and the exit pressure of the evaporator is sensed by the power fluid, and the degree of superheat is fixed accordingly. Okay. So if there is a large pressure drop across the evaporator, then you find that the exit pressure evaporator exit pressure will be very low, and the corresponding saturation temperature at the exit also will be low. So you find that the actual superheat at the exit will be much higher than the set superheat. Okay, because the actual superheat is nothing but the set superheat plus temperature drop due to pressure drop. Okay, and that means you find that in the actual case, because of the large pressure drop, most of the evaporator area is dry because of the larger superheat. That means evaporator will not be utilized properly. Okay. In addition to that, when you have a large superheat, system performance also will be affected adversely. Okay. So to correct for this, a thermostatic expansion valve is provided with a tapping which feeds the pressure PE minus delta PE from evaporator exit to the bottom of the bellows. So what we do is to take care of this one, instead of sensing the inlet pressure of the evaporator, the modified thermostatic expansion valve will work based on the exit pressure of the evaporator, not based on the inlet pressure of the evaporator. Once it is based on the exit pressure of the evaporator, then you find that the actual superheat will be the set superheat. Okay. Let me show a picture. Okay, so this is the schematic of a thermostatic expansion valve with external equalizer. Okay, this is called as external equalizer. The difference, as you can see here, is the, let us say that this is a bellows. Okay, let me just say that this is a bellows, right. So here the pressure acting is pressure due to the feeler bulb, that is PP, and the downward pressure is not the pressure at the inlet of the evaporator, but that is the pressure at the outlet of the evaporator. Okay, that means you take a pressure tapping at the outlet of the evaporator, and that pressure will be acting below the bellows. Okay, so this is called as the T with external equalizer. Normal evaporator, what happens is this partition will not be there, so the pressure acting here will be inlet pressure itself, P inlet. Okay, in the normal this thing, but when there is a large pressure drop, we modify this one and we go for this kind of external tapping. Okay, so that the pressure opposing this one will be PE minus delta P. Okay, not PE, right. So this will result in a degree of superheat equal to the set value delta Ts. A T with this provision is called as thermostatic expansion valve with external equalizer. Since larger pressure drop leads to low COP, normally large evaporators have a number of parallel refrigerant paths. Of course, this does not really solve the problem. That means if you have a very large pressure drop, you have designed the system in such a way that you have a very large pressure drop in the evaporator. Okay. If you are taking care of it by providing a thermostatic expansion valve with external equalizer, that will solve the problem of the thermostatic expansion valve, but that will not improve the performance of the system as such, because large pressure drop across the evaporator is not good from the performance point of view. So in actual practice, what is done is, whenever there is a large evaporator with large evaporator length, normally parallel paths are provided. Okay, that means instead of using a single path, the refrigerant is split into parallel paths. So thereby you can reduce the flow rate through each path, and the length of the each path also can be reduced. Thereby you can reduce the pressure drop across the evaporator. Okay. So if a single, even then a single thermostatic expansion valve fitted with a distributor supplies refrigerant to the different paths. That means you can have a same, if you have a evaporator with multiple paths, you don't have to have many thermostatic expansion valves. A single expansion valve is enough. Okay, but you have to use a distributor along with the thermostatic expansion valve, which will distribute the refrigerant into different paths. Okay. So that was the first variation available, and the second variation is what is known as thermostatic expansion valve with cross charge. If the power fluid used in the feeler bulb is same as the refrigerant in the system, then for the same mass flow rate, that means I fixed delta PS, the degree of superheat will be much smaller at higher evaporator temperatures. That means, as I said in the example I have shown you, let us say that you have a refrigeration system which uses R12 as a refrigerant, and you have a thermostatic expansion valve which also uses R12 as the power fluid. Okay, this is what is known as a straight charged thermostatic expansion valve. That means the refrigerant and power charge, power fluid, both are same. Okay, when both are same, you will find that at higher evaporator temperatures the degree of superheat will be much smaller than the degree of superheat at low evaporator temperatures. Okay, but that means for the same spring force, the degree of superheat will be different at different evaporator temperatures. Okay, so let me show this with the help of a schematic. You can, this is the saturation curve. Okay, saturation curve, that is Psat, and this is pressure versus temperature. Okay, so you can see that, let us say that I have fixed the spring in such a way that I get a delta PS due to spring. This is equal to PP minus PE. Let us say that I have set it as 0.3 bar. Okay, I have fixed this at 0.3 bar, and when the evaporator temperature is minus 40 degrees centigrade, then you will find that for this 0.3 bar pressure difference, you get a degree of superheating of 10 Kelvin. Okay, how do you get this degree of superheating of 10 Kelvin? All that you have to do is you have to find out this pressure. This pressure corresponds to saturated pressure at minus 40 degrees centigrade. Okay, so you get some pressure value, and then you have to get this temperature. And how do you get this temperature? This temperature is nothing but saturation temperature at evaporator pressure PE plus 0.3 bar. Okay, so in one case you use the temperature to find the saturation pressure, and for finding the superheat temperature you have to use the pressure values and then find this temperature. So the degree of superheat is nothing but this temperature minus this temperature. So you find that at minus 40 degrees centigrade the degree of superheat is 10 Kelvin. Now if the same system operates at minus 20 degrees centigrade, and if you have not changed the spring force, then again the pressure difference will remain 0.3 bar, then you find that the degree of superheat reduces to 7 Kelvin. Okay, that means from 10 Kelvin it reduces to 7 Kelvin. Now if the same system is operated at 5 degrees centigrade, and again the same spring force is maintained and the same pressure difference is maintained, you find that the degree of superheat has reduced to 3 Kelvin. Okay, that means as the system operates from minus 40 degrees centigrade to 5 degrees centigrade, the degree of superheat has reduced from 10 Kelvin to 3 Kelvin. So you will find that if you operate it at much higher evaporator temperature, the degree of superheat becomes very, very small. Okay, so at higher, at still higher TE, you will find that degree of superheat will be very, very small. Okay, that means it almost approaches 0. Okay, and first of all, where do you encounter this kind of a situation where the same system is operated over such a large evaporator temperatures? You may not during the normal design condition you may not operate the system under such a high evaporator temperature variation. Okay, but when the system is started or during the pull down, during each pull down the evaporator temperature has to begin from a very warm temperature and it has to come back to its design temperature. Okay, so during every pull down you will find that the evaporator temperature is varying from a very high value to a very low value. Okay, this kind of a situation is encountered, for example, in a freezing unit. Okay, in an ice cream making unit or some other freezing unit, or even in a domestic refrigerator, where the freezer is maintained at about minus 20 degrees centigrade or so. Okay, so during every pull down this thing, the evaporator temperature has to start right from the ambient temperature of say plus 30 degrees centigrade, and it has to come down to minus 20 degrees centigrade. Okay, so you find that there is a large temperature variation. Okay, so if you have set the degree of superheat at minus 20 degrees centigrade, then you find that when the system is operating at higher evaporator temperature, the degree of superheat becomes almost 0. Okay, now what is the problem when the degree of superheat becomes very small? When the degree of superheat becomes small, as I said, when the plant is started at warm temperature, there is a possibility of flooding of evaporator due to very low delta Ts. Okay, so if degree of superheating is not sufficient, then more refrigerant may enter. Okay, and there is no load, or higher refrigerant flow will be there to the evaporator. So evaporator may get flooded, and flooding, as you know, may lead to slugging of the compressor. Okay, so this has to be avoided, right? So if the now one way of avoiding this is to increase the degree of superheat at higher evaporator temperatures. Okay, that means what you can do is you set the spring force in such a way that at higher evaporator temperature you increase it to, let us say, 10 Kelvin. Okay, that means you have to increase the spring force, or you have to increase the delta Ps. Okay, so you increase the delta Ps in such a way that at higher evaporator temperatures you are getting higher degree of superheat. So this will take care of the problem of flooding. But what happens when the evaporator comes to the design evaporator temperature? You will find that when it is operating at the design evaporator temperature under the higher degree of superheating, you will find that this degree of superheating may become 20 Kelvin or more. Okay, I am just giving an example, right? That means the degree of superheat becomes very, very large at low evaporator temperatures. And as you know that when the degree of superheat is becoming very large, most of the evaporator area is simply being used for sensible heating of the refrigerant. Okay, that means the heat transfer rate will be very low and the system efficiency will be poor. Okay, so this is the problem. So if you set the degree of superheat for lower temperature, then you may have a problem of flooding when the evaporator temperature is high. Okay. On the other hand, if you set the degree of superheat for higher temperature, then the degree of superheat may become very large at a lower evaporator temperature, and this may lead to the starving of the evaporator and poor performance of the system. Okay. So what is the solution? All this is happening because we have used the same fluid in the feeler bulb as that of the refrigerant system. Okay. So one alternative is to use a different fluid in the feeler bulb. Okay, that means the problem can be corrected if a fluid different from the refrigerant is used in the feeler bulb as power fluid. Such a thermostatic expansion valve is called as thermostatic expansion valve with cross charge. The power fluid is selected such that at any temperature it has lower saturation pressure than that of the refrigerant in the system, so that as the evaporator temperature increases, the degree of superheat also increases. That means we use a different fluid in. Okay. So this again shows the saturation curve. For example, this is the saturation curve of the refrigerant. Okay, and this is the saturation curve of the, as you can see, the power fluid, right? And you can see that at any temperature the power fluid has a lower saturation pressure corresponding to the refrigerant. Okay. So what is the advantage of this? The advantage of this is like this. You can see that if you are operating the system at this evaporator temperature, and if you have this, if you have set the spring force such that the pressure difference is delta Ps, then this is the degree of superheat. Okay. And how do you get the degree of superheat? You know this temperature, so you can find out this pressure. Okay. And you know this delta Ps, so you can find out this pressure, and this temperature is obtained from the saturation temperature characteristics of the power fluid, not the refrigerant. Okay. So if you know the characteristic, then you can find out this temperature. Okay. So from that you can find out what is the degree of superheat. Now this is the degree of superheat at low evaporator temperature. At high evaporator temperature also you find that the degree of superheat is much larger than when you used same fluid as the power fluid. That means, for example, if the same fluid is used as a power fluid, then this would have been the degree of superheat. Okay, because this is the delta Ps, this would have been the delta Ts with the straight charge, that means with the same fluid as that of the refrigerant, but by using the cross charge we could maintain a high degree of superheat even at higher evaporator temperatures. Okay, so that is the advantage of using cross charge. Okay, so whenever you have the problem of operating the system over a wide evaporator temperature range, normally you use a cross charged thermostatic expansion valve. Okay. Of course, cross charge valves perform satisfactorily in a narrow range of temperatures. It does not mean that it will operate satisfactorily over any temperature range, but it operates satisfactorily over a certain temperature range only. Okay. And when you are selecting the valve, you must specify the range of operation. Okay. Now the third variation is possible depending upon the amount of power fluid present in the feeler bulb. Okay. So based on this, you can have a thermostatic expansion valve with what is known as a normal charge. What do we mean by normal charge? Normal charge means the feeler bulb is charged with about 50% of liquid and 50% vapor. So when you have this kind of a normal charge, there is always some liquid in feeler bulb. Once there is some liquid in feeler bulb, always you will find that the bulb always controls the operation of thermostatic expansion valve. And this kind of a thermostatic expansion valve is good during normal operation, but you will find that when you are using the normal charge, there is a possibility of compressor getting overloaded during pull down time. Okay, as the thermostatic expansion valve is kept wide open during pull down due to high temperature, which will lead to high mass flow rates. Okay, so let me explain this. I hope you remember the pull down characteristics of the compressor. Anyway, let me just quickly draw it. We have seen while discussing the compressor characteristics that you have this kind of a let us say this is evaporator temperature variation, then the compressor power varies in this fashion, right. And if you are starting the system at this point during the pull down, normally the system will be temperature will be high, and let us say that your design temperature is somewhere here. Okay, this is your T design, and this is your temperature at the beginning of the pull down, right. So if you remember, if you are operating the system like this, the power requirement first increases sharply like this, right, and it reaches a peak, then it comes down, okay, and finally comes to the design point, right. That means you find that if you have if you remember, if you have selected a motor which will operate satisfactorily at the design point, that means if your motor gives only this much power, design power, then you find that during this portion the motor is overloaded, right. So this is what is known as motor overloaded during the pull down time. Okay, this happens if you remember because of the fact that during the pull down time the mass flow rate of refrigerant will be very high, because the compressor volume pressure ratio will be small, so it will operate at high volumetric efficiency, and also the density of the refrigerant will be high. Okay, so initially the mass flow rate of refrigerant through the compressor will be very large, even though the enthalpy difference across the compressor is small. Okay, since the mass flow rate is very small, very high, the power requirement will be very high in the beginning. Okay, after some time, as the pressure ratio increases, the mass flow rate through the compressor reduces, so the power requirement also reduces. Okay, that's how we get this kind of a curve, right. So the power peak or the motor overload is taking place because of the higher mass flow rate. Okay, and when you are using a thermostatic expansion valve with normal charge, the feeler bulb will always sense the temperature at the exit of the evaporator, which will be very high during the pull down time. Since this temperature is high, the pressure inside the feeler bulb will be very high. Once the pressure inside the feeler bulb is high, the pressure acting on the bellows will be high. That means the bellows will be pushed down, that means the needle will be pushed down, there will be higher area available for refrigerant to flow, so there will be higher flow rate. Okay, since there is a higher mass flow rate, the power requirement of the compressor also will be high. Okay, so if you have not designed the motor properly, then there is a danger of motor getting overloaded, right. So this is the problem with normal charge. Okay, otherwise normal charge is very good during normal operation. So you have the second possibility, that is what is known as limit charge or gas charge. So here the amount of power fluid charged is small, and at a particular temperature all the power fluid will be in vapor form. Okay, this is known as fade out point. and for a given temperature rise, the rise in pressure after the fade out point is very small. Okay. So, as I said, let me explain this. Okay, so this system is for the limit charge system. Okay, so up to this point you have in the bulb, let us say that this is a feeler bulb. Okay, so you have liquid plus vapor. So as the temperature increases here, this liquid will evaporate, right? And you have charged the liquid in such a manner that at this point all the liquid will evaporate, right? Once all the liquid evaporates, you have only vapor in the feeler bulb. Okay, that means from this point onwards, the pressure variation will not be along this saturation curve line, but along this line. Okay, this line corresponds to the pressure rise because of the temperature rise only, because of not because of evaporation or anything. And you find that during this portion, the rate of change of pressure with temperature is much smaller compared to this one. Okay, that means what? That means from this point onwards, your delta P by delta T will be small. Okay. This is small means what? The needle opening will be small. The needle opening will be small means mass flow rate of refrigerant doesn't vary much. Okay, that means from beyond this point onwards, if you write, let us say that delta mass flow rate divided by delta T, let us say this will be small. Okay, because from this point onwards you don't have any more liquid, right? Okay, so beyond the fade out point, no further increase in flow rate. So what is the advantage of this? If there is no further increase in flow rate beyond this point, the overloading of compressor can be avoided during pull down time. Okay, so the advantage of using this limit charge valve or gas charge valve is that whenever the system operates during the pull down, you find that the valve will not open beyond a certain point. Okay, whatever be the temperature, right? That means the flow rate reaches a particular value and it will not increase beyond that point. That means you are restraining the power input or power requirement of the compressor. Thereby you can avoid the overload of the motor. Okay. However, there is a one problem with this, that you have to take care that the thermostatic expansion valve body should not be colder than the feeler bulb to avoid condensation of power fluid above bellows. Otherwise, the thermostatic expansion valve loses sensitivity. What does it mean is, let us say that this portion is much colder than this portion. Okay, and when you have only vapor here, then since this portion is colder, all the vapor will come here and it will collect here in a liquid form. Okay, it will condense here. Once it condenses in liquid form here, this will lose the sensitivity. Okay, so it will not respond properly to the suction line temperature. Okay, so this has to be avoided. That means this portion should not be colder than this portion. Okay, then finally you have what is known as the liquid charged. Liquid charge means here the complete power element, that means the feeler bulb plus connecting tube plus volume above the bellows is filled with liquid. Once you fill it with liquid, the valve simply operates as a hydraulic valve and there is no vaporization of liquid. And when do you use this kind of valve? This kind of valve is very rarely used, but this is used where the bellows or the thermostatic expansion valve body is always exposed to very low temperatures. Okay, so whenever you cannot avoid keeping it in a very low or temperature environment, then you can go for liquid charged bodies where the problem of condensation will never arise because always you have only liquid, right? Okay, so these are the various variations available with thermostatic expansion valves. Now let us look at selection of thermostatic expansion valve. Thermostatic expansion valves are normally selected from manufacturers' catalogs based on application, refrigeration capacity and type of working fluid. Okay, so manufacturers give catalogs to suit various applications and various loads, etc. And the design of thermostatic expansion valve could be different to suit different requirements such as single evaporators, multi evaporators, etc. Now there are certain precautions you must observe while installing the thermostatic expansion valves. What are the precautions? First is the location and actual mounting of feeler bulb. This is very important. Feeler bulb must be in good thermal contact with the refrigerant tubing. Let me give a small example why location is important. For example, let us say that this is your refrigerant tubing. Okay, here you have the evaporator. Okay, and refrigerant is flowing through here. Okay, and feeler bulb you must keep somewhere here in this portion, right, beyond this point. Suppose you are keeping the feeler bulb like this, right. This is the wrong way of installing, because if you are keeping the feeler bulb like this, you find that the liquid is not in contact with the bulb. Okay, liquid, because the gravity will settle down, and what is in contact with the tube is vapor. Okay, once the vapor is in contact with the tubing, it will not respond properly to load changes. So the valve will not be sensitive. So what is the correct way? The correct way is to keep the valve in this manner, feeler bulb in this manner, so that liquid will always remain in contact with the refrigerant tubing and it will respond properly to the load variations. Okay, that is what is the meaning of keeping the feeler bulb, mounting the feeler bulb properly. Okay, and there must be some good thermal contact between this, otherwise the temperature here and temperature here will be different if there is no good thermal contact. Okay, so there must be perfect thermal contact between the bulb and the refrigerant tubing. And surface of feeler bulb and refrigerant tube must be free from rust scale before assembly. Okay, a rust or scale will offer thermal resistance, again the temperature difference will be more. Okay, so that must be avoided. And the bulb should preferably be insulated from outside environment, okay, for good sensitivity. And what are the salient features of thermostatic expansion valves? It provides excellent flow control. Evaporator operates efficiently, because we have seen that you can control the superheat properly. That means you can avoid both starving as well as flooding of evaporator. And this valve ensures a minimum amount of superheat, and thereby it avoids slugging of compressor. Of course, provided you select the thermostatic expansion valve suitably. Okay. However, there are certain disadvantages. Disadvantages are this valve is relatively expensive compared to other types of valves, and this valve cannot be used in applications where a close approach between the fluid to be cooled and evaporator temperature is desired due to requirement of a minimum amount of superheat. That means when you want the external fluid temperature to be very close to the refrigerant temperature, then you cannot use this kind of valve, because this kind of valve will always maintain a certain amount of superheat. Okay. So generally you cannot use this one. Of course, one possible solution is to have a perfect counterflow type of evaporator, okay, where you can have close approach, yet you can use thermostatic expansion valve. Okay. Now let me quickly explain the float valve. Float valves are normally used in large systems with flooded evaporators. The valve opens or closes depending upon the liquid level as sensed by a buoyant member. The buoyant member is called as the float, and this float can be a hollow metal ball or a hollow cylinder or a pan. This float valve you must have seen, normally we use it for this kind of a float valve in our water tanks and all, okay, to prevent the overflow of water in overhead water tanks. Okay. The refrigerant float valve is also somewhat similar in operation, right. And the float valve always maintains a constant liquid level in a chamber called as a float chamber. The float chamber may be placed on the low pressure side, then you can call it as a low side float valve, or on the high pressure side, in which case you call it as a high side float valve. Now let us look at the low side float valve. The low side float valve maintains a constant level of liquid refrigerant in the evaporator. This type of valve is used with a flooded type of evaporator. If you remember, I have discussed this while discussing flooded type of evaporators. This is the low side float valve. Okay, so this is your float chamber, and this is the flooded type evaporator. Okay, and this is your float, right. So you can see that this is a flooded type of evaporator, and this float valve will always maintain this liquid level. Okay, what happens when the liquid level drops? First of all, when this liquid level drops when the load on the evaporator increases. Let us say that load on the evaporator is increasing. When the load on the evaporator increases, this evaporation rate increases, so higher mass will leave the float chamber. Higher mass leaves the float chamber means this level will drop. Once this level drops, that is sensed by this float, and this will open the float valve wider. Okay, there will be wider opening of the float valve. Once the float valve is opened wider, more refrigerant will flow into the float chamber, and the level is restored. Okay, and the reverse happens when the load falls and the level rises. When the load falls and the level rises momentarily, then this float will move up. Once the float moves up, this valve will be closed. Once this valve is closed, not fully, but the opening becomes narrower. Once this opening becomes narrower, less refrigerant enters into the float chamber, again the level is restored. Okay. So, this is what I have explained. When refrigerant load increases, liquid level falls momentarily, float valve opens wider, allowing more refrigerant to flow, thus restoring the level. The opposite happens when the refrigerant load decreases. So, the high side float valves, this maintains a constant liquid level in the high side float chamber. Okay, this is placed at the exit of condenser. That means you have a high side float chamber. This is placed between the condenser and the evaporator. Okay, so this is the high side float valve, right. So, refrigerant enters from the condenser, it first comes to the high side float valve, then it flows through this float chamber, then it flows to the float valve, and through the float valve it enters into the evaporator. Okay. Now, let me quickly explain, and this float valve will always maintain this level. Okay. What happens when the load increases or reduces? Let us say that you have the evaporator here, okay, and the load on the evaporator increases. When load on the evaporator increases, more refrigerant will boil. Once more refrigerant boils, more refrigerant will condense here, that means more refrigerant will flow into the high side float chamber, that means the level will increase here. When the level increases, this float valve is such that it will open more, okay, that means when the level increases, opening will be wider. When the opening is wider, more liquid will flow through the valve into the evaporator, okay. That means when QE increases, wider opening, okay. Wider opening means higher flow rate, and similarly when QE reduces, there will be narrower opening, right. So, that is how the level is controlled, and thereby the load is taken care of. Okay. So, this is the principle of high side float valve. You can see that both low side float valve as well as high side float valve responds to the load in a proper manner. That means when the load increases, they supply more mass flow rate, and when the load reduces, they supply less mass flow rate. Normally the float valves, as I have already mentioned, is used along with flooded type of evaporators, and flooded type of evaporators are very efficient because of high heat transfer rates and all. So, they are mainly used in large refrigerant systems. So, you find that in large refrigerant systems, the expansion device used is normally the float type of expansion device. Okay. Okay, I have already explained this. When refrigerant load increases, more vapor is generated in evaporator, condensation in the condenser increases, which increases the level of liquid in the float chamber. Valve opens more to allow more liquid into evaporator. But unlike low side float valve, the high side float valve can be used with both dry as well as flooded type of evaporators. Now, let me quickly explain another type of expansion valve, which is known as electronic expansion valve. This electronic expansion valve consists of a thermistor which senses the presence or absence of liquid refrigerant at the exit of evaporator. First of all, what is a thermistor? Unlike a resistor, I am sure that you know that for a thermistor, as the temperature increases, resistance decreases. Okay, so this is the principle of thermistor, right. So, this electronic expansion valve uses a thermistor, and this thermistor senses the presence or absence of liquid refrigerant at the exit of evaporator. If liquid is present, when liquid is present during reduced load condition, all the refrigerant may not evaporate. So, there could be some liquid at the exit of the evaporator. When liquid is present, then thermistor temperature decreases and its resistance increases. Okay. So, let me show the picture now, it will be clear. So, as I told you, you have this is the body of the electronic expansion valve, and it consists of a heater which is in series with a thermistor, and this thermistor is located at the exit of the evaporator, you can see that. So, this senses the exit temperature of the evaporator, okay. And as I said, when there is liquid here, okay, once liquid is there, there will be good heat transfer here, and the thermistor temperature will be low. When the thermistor temperature is low, its resistance increases, and when you are applying a fixed voltage across the circuit, you will find that since this resistance is increasing, the current reduces, okay. And since the heater is in series with the thermistor, the current through this heater reduces, okay. Once the current reduces, the heating output reduces. When the heating output reduces, this will move up, the needle moves up, and there will be less refrigerant flow through the electronic expansion valve. Once the less refrigerant flows through the expansion valve, at a balance point the liquid vanishes, again this temperature increases, then the resistance again reduces, there will be higher current and there will be wider opening, okay. So, that is the principle of electronic expansion valve. So, you can see that it has a heater, a thermistor, and you have to apply a fixed voltage, okay. So, as I said, the current through the heater which is in series with thermistor decreases when the load increases and the valve opening becomes narrower. I am sorry, when the load decreases, the valve becomes narrower, and due to the narrow opening, mass flow rate of refrigerant decreases. Okay, and reverse happens when there is no liquid. The control of electronic expansion valve is independent of refrigerant and refrigerant pressure, because unlike other expansion valve, this is the specialty of this type of expansion valve. It does not depend on the type of refrigerant used and the refrigerant pressure. Okay, so it can work in reverse direction also. As a result, this kind of valves are can be used in year-round air conditioning system, which work as air conditioners in summer and as heat pumps in winter. Okay, when it is working as heat pump in winter, you have to reverse the refrigerant flow direction. Okay, so that is possible when you are using electronic expansion valve. And in another version, the heater is replaced by a stepper motor which opens and closes the valve with a great precision, giving a proportional control in response to temperature sensed by the element. Okay, that means in the more modern versions, you can replace the heater by a stepper motor, and this stepper motor operation is controlled by the thermistor. Okay, so you can have a modulating control, okay, or you can have a proportional control, so you can very finely control the refrigerant flow rate. Of course, electronic expansion valve compared to other types of valves are quite costly, okay, and they are not really very widely used because of this reason. Now, let me quickly look at some general rules to be observed while selecting and installing expansion devices. The valve capacity should be neither too large nor too small. When the capacity is too large, that means you have selected a very large valve, you will find that the valve will overfeed refrigerant, and this may cause flooding and slugging. And this may also result in hunting. Hunting means frequent closing and opening. Okay, these are the problems with large valve. And what are the problems with small valve? If you select a small valve, this will result in insufficient capacity, that means starving of evaporator, and balance point at low evaporator temperature. Okay, so you have to select the right valve depending upon your refrigeration capacity. And the second point is operation during winter. Since condenser pressure is low during winter, the pressure difference across the expansion valve will be low. Okay, hence balance point occurs at lower evaporator temperature. Remember that for an expansion device other than your electronic expansion device, the flow rate is proportional to flow area and also the pressure difference between the condenser and the evaporator. So, during the winter, condenser pressure will be low because the heat rejection temperature will be low, so condenser pressure reduces. Once condenser pressure reduces, your pressure difference across the expansion device reduces. Once the pressure difference across the expansion devices reduces, mass flow rate reduces. So, the balance point will be established at a lower evaporator temperature, so that again the Pc minus P, that is the pressure difference across the valve, is sufficient. Okay. So, you will find that in winter the expansion valve will be operating at lower condenser temperature and also lower evaporator temperature, and you know that operating at lower evaporator temperature is not efficient because this will lead to poor COP, etc. Okay, so this is one of the problems with this kind of expansion devices. So, this decreases the efficiency of the system. To prevent this, sometimes the condenser pressure is kept artificially high during winter months. Okay. So, you will actually lose the advantage of operating the condenser at lower condenser temperatures because of this limitation of the expansion devices. Okay. And the third point is inlet to expansion valve should always be liquid, that means you must always feed liquid refrigerant to the expansion device. So, to ensure this, you must have a liquid seal at the inlet to the expansion device, and valve should not be located at very high elevations to prevent flashing due to drop in static pressure due to gravity. Okay, that means when you have the condenser here, let us say that your condenser is here, and if you are keeping the valve here, okay, acceleration due to gravity is like this, and this is your expansion device, this is the condenser, then the refrigerant has to flow from this point to this point. Okay, so there is a large height. Okay, so the pressure at this point will be less than the pressure at this point due to the static head. Okay, and if this pressure difference is too small, too large, then during the flow from this point to this point, some flashing may occur and some vapor may enter into the expansion device. Okay, so this has to be avoided. Okay, it at not very high elevations, and a liquid suction heat exchanger also will minimize this problem to a large extent. Okay, so these are the practical problems and practical points to be considered while using and installing the expansion devices. Thank you.